Hello.
Hello, sir.
Yeah. Hi. So we'll continue with surface tension. We are in section number 14.9.
Yeah,
So last class I was asking why is the surface tension force there? So the reason you guys must have read through, right?
yes, sir.
Yeah.
So the reason is that the forces on the molecules are different on the two sides. So for example, this is a top layer of a liquid, let's say, right?
Yeah,
Inside there is many other molecules. Outside there are air molecules, right?
Yeah.
yeah,
So now between air molecules and liquid molecules also there is some force. There is an attractive force, let's say, some amount of it, right?
yeah,
Hmm.
yeah,
But these two molecules are different kinds, right? Different kinds of molecules.
Kinds. Yeah.
So those types of attractive forces are called adhesive forces. Adhesive forces are forces between two different kinds of molecules, and these are similar kinds of molecules in the lower layer, right?
Hmm.
yeah, yeah,
Those also attract the top layer.
Yeah.
Those forces are called cohesive forces, force of cohesion. That is between similar kinds of molecules, the attractive forces, right?
yeah,
Yeah.
yeah.
Now, clearly, this molecule and this adhesive force and cohesive force don't have to be the same, right?
Hmm.
Because
Yes, yeah,
most likely they will be different because this molecule and air molecule will have a different force than this molecule and this molecule, right?
yeah,
Yeah.
yeah,
Yeah.
So most likely they are different, and usually what happens is cohesive forces are stronger than adhesive forces.
That's it.
So there is a tendency to shrink that top layer. Top layer wants to come inside, right?
Yeah.
yeah, yeah.
The top layer wants to come inside. That means you're trying to shrink the top layer. That is the surface tension force. Okay.
Hmm.
Mm-hmm.
So surface tension is the result of asymmetric distribution of molecules on both sides of the surface, right? Is
Yeah,
as a result of asymmetric types of molecules, right?
Yeah.
Asymmetric molecules on two sides. So one side is molecules of air, one side is molecules of water or fluids, right?
yeah,
So therefore, the forces that they exert are going to be different, and the resultant force that happens will try to pull or push the surface, right?
mm-hmm.
Yeah.
That force is the surface tension force.
Surface tension.
Now, he explains this also here below figure 14.13. So he takes a drop of water or something, and he says, in this drop of water, on this water surface that is there, if you draw a line, right? Suppose a line AB is drawn on that water surface, right? Now this line AB therefore partitions the water surface into two halves. This is the left half and this is the right half, right?
Yeah,
Yeah.
So now it is found that the two halves will pull each other with some force like this. So left half pulls the right half like this, and right half pulls the left half like
Left hand.
this,
Yeah.
which is equal and opposite forces according to Newton's laws, and they are perpendicular. Forces are perpendicular to the line AB,
Yeah.
yeah,
Yeah.
yeah,
perpendicular to the line AB and tangential to the surface. Tangential to the surface means if the surface was like this, force is like this, right? Tangential.
right, right, yeah,
Think of it in 3D. Surface is a 3D thing, and the force is tangential along this line, right?
Yeah.
yeah, yeah,
Okay. So that force is found to be proportional to the length of the line L. This force is found to be proportional to the length of line
Yeah.
L. Okay. So this is an experimental verification. People found that there was a force that attracts, force by which this part of the surface, the left part, attracts the right part, and the right part attracts the left part. And later it was found that it was proportional to the length of that line.
Hmm. Hmm.
So that means that force will be equal to some constant of proportionality into L, right?
Yeah, yeah.
This constant of proportionality is also called surface tension. So S can be written as F by L. S can be written as surface tension is F by L. For force of by which the surface parts are pulling each other divided by the length of the line across which they are pulling.
Yeah.
So unit of that surface tension will become Newton per meter, right?
Yeah, yeah.
Yeah.
Now, there are multiple experiments here, A, B, two experiments that he has explained how you can demonstrate the property of surface tension, right? He has taken some rubber, there's a ring of wire and stuff. He has dipped it into soap solution and stuff. So
Yeah.
you should read through this A and B. That is not difficult to understand. Then we will go over to the next part, which is tendency to decrease the surface area. So right now, this is one way to define surface tension, which is force, tangential force across a given line of length L, right?
Yeah, yeah.
This is one way to describe surface tension. There is another way to define surface tension also, which is in terms of the tendency to decrease the surface area. Although both ways are actually the same thing, because when those force is acting, it's trying to shrink the surface area.
Yeah.
Right, yeah.
Right. So now he says the property of surface tension may also be described in terms of the tendency of a liquid to decrease its surface area. Because of the existence of forces across any line in the surface tends to shrink whenever it gets a chance to do so, right? The two
Yeah.
demonstrations above may help us in understanding the relation between the force of surface tension and the tendency to shrink the surface. Okay. Um, this is fine. Let's go ahead and talk about surface energy, right? So
Right.
14.10 is surface energy, where 14.10 he says we have seen that a molecule well within the volume of a liquid is surrounded by similar liquid molecules across all sides, and hence there is no resultant force on it. So if you are inside the body of a liquid
Yeah.
and not near the surface, right, then
Yeah.
you will be facing resultant force will be zero, right? There will be
Yeah,
no
yeah.
net force on you because on all sides you're facing similar molecules. On the other hand, a molecule in the surface is surrounded by similar liquid molecules only on one side, while on the other side there is air molecules, right? The vapors having much less density, only air molecules also, or molecules of the vapor of the liquid, right? Vapor pressure, right?
Yeah, yeah.
Yeah. Yeah.
Those two things can be there on the top, right? And these vapors, since they have very less density, exert only a small force. Therefore, there is a resultant inward force on a molecule on the surface, right? This
Yeah, yeah.
force tries to pull the molecule back into the layer, back into the liquid. Thus, the surface layer remains in microscopic turbulence. Turbulence means it constantly molecules on the surface want to come inside, right?
Yeah, yeah.
Okay, so molecules are pulled back from the surface layer to the bulk, and new molecules from the bulk go to the surface layer to fill the empty space. So constantly that process is happening. Now, when a molecule is taken from inside to the surface layer, work is done against the inward resultant force while moving up in the layer, right?
Yeah, yeah, yeah.
So for example, you have, this is the surface and this is the bulk here, right? Here, resultant force was zero, but surface molecules are facing a force like this, right? Correct?
Yeah.
Yeah.
So if a molecule is taken from here and taken to this surface, there is work done on it which is negative, right? Which is against this force, right? Like it actually wants to go down. If you are bringing it up and up, it will face forces downward, right?
Yeah.
But it is going up, right? So someone is doing work on it and it is going up, right? So you are raising its potential energy, sort of, right? and bringing it to this point, because
Yeah.
this is the stable U is the zero in this situation, right?
Yeah.
Correct. So he's saying work is done against the inward resultant force while moving up in the layer. The potential energy is increased due to this work, right?
Yeah.
A
Yeah.
molecule in
Yeah.
the surface has greater potential energy than a molecule in the middle of the liquid, right?
Yeah.
This extra potential energy is called surface energy. Surface
Yeah.
energy, which is as a consequence of it being on the surface, right?
Yeah.
Yeah. Yeah.
Now, the surface energy can be related to surface tension by this experiment. So he's saying take a U-shaped frame with a sliding wire, U-shaped frame with a sliding wire, and dip it in soap solution and all, right?
Hmm.
So if you dip it in soap solution, a thin film will appear on it.
Yeah.
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 Now, that film may look thin to our eyes, but actually, the thickness of that film will incorporate hundreds of thousands of molecular layers, right?
Hmm.
Correct.
Yeah.
Even if it is 1 mm, there's hundreds of thousands of molecular layers here, right?
Yeah.
Right.
Yeah.
So that film actually, if it is this thick, it has two surfaces, one the top surface and one the bottom surface, right?
Yeah. Yeah.
Yeah. Yeah.
You understand? Correct.
Yeah.
And it is connected to the wire here with two surfaces basically, one top surface and one bottom surface, right?
Right. Right.
Right.
You understand what I'm saying? Dip
Yeah.
it in
Yeah.
film, you will have a soap film connected across this portion.
Yeah.
But what looks like one layer to you is actually multiple layers, because that is molecules are very small, right?
Yeah.
So
Yeah.
there is a top layer there is a bulk portion there in the middle, and then there's a bottom layer also.
Yeah.
Right?
Yeah.
Now, on this line, if this line has length L, each surface will exert a force of S into L, right?
Right. Yeah.
Yeah.
Inward pulling force, because it wants to shrink its surface area, right?
Yeah.
So this is from the surface tension discussion earlier, that any line on the surface, it pulls with SL, right?
Yeah. Yeah.
But there are two surfaces, so the total inward force will be 2SL.
But sir, there are so many layers, right?
No, but any point in the middle, right, that is not behaving in a turbulent way, the bulk.
Right. Okay. Okay.
The bulk portion is not behaving in a turbulent way, because actually the bulk is in equilibrium. The top surface and all you are trying to shrink.
Right. Right.
Okay, the top surface is the surface that matters, and the bottom surface is the surface that matters.
Yeah.
Okay.
Okay. Yeah.
So,
Yes, sir.
so 2SL is the force of surface tension, and so therefore to keep the wire stationary, you have to exert F force. F is equal to 2SL, right?
Yeah. Yeah.
Correct. So he's saying the soap film that is formed may look quite thin, but on the molecular scale, its thickness is not small. It may have several 100,000 molecular layers. So it has two surfaces enclosing a bulk of soap solution. Both the surfaces are in contact with the sliding wire and hence exert forces of surface tension on it. If S be the surface tension of solution, L is the length of sliding wire, each surface will pull the wire parallel to itself with a force of SL, right?
Yes. Yeah.
Each surface pulls the wire parallel to itself with a force of SL. Okay.
Right. Yeah.
The net force of pull on the wire due to both the surfaces 2SL. Therefore, one has to apply an external force equal and opposite to F so as to keep the wire in equilibrium, right? Now, suppose you pull out the wire by a distance X, right? So that the area of the frame you have pulled it out by a distance X, right?
Yeah.
Yeah.
The area of the frame has increased by L into X. This area has increased, no, LX.
Yeah. Yeah.
Yeah. Yeah.
As there are two surfaces of the solution, a new area of 2LX is created, right? New surface area of 2LX actually has been created, because LX on one surface, LX on the other surface, right?
Yeah. Yeah.
Correct? So work done by external force in this case will be F into X, right? Because F is the constant force you have to pull against, right?
Yeah.
Work done by external force is 2SLX, right?
Yeah.
Now this work should show up as energy that is extra energy that is there in the surface, right?
Yeah.
This work should show up in the extra potential energy of the solution of the film.
Solution. Yeah, yeah.
But extra potential energy is appearing because of extra area that came here, right?
Yeah.
Right? So we
Oh.
can say that U, extra potential energy, is equal to work is equal to 2SLX, right? But
Right. Yeah.
you can also say S is equal to U by 2LX, right?
Yeah.
Mm-hmm.
And this is U by the extra area, right?
Yeah. Yeah.
Yeah. Mm.
Correct. So this expression basically says surface tension can be written as extra energy generated by extra area created, right? Or potential energy extra that came out, right?
Yeah.
Divided by the extra area that was created, right?
Right. Yeah.
So potential energy per unit area, right? So that therefore surface tension can also be defined in terms of surface energy by area, right?
Yes. Yeah.
Yeah.
So we see that increase in surface energy is U is equal to W is equal to S into 2Lx, and U by 2Lx is S, U by A is S,
Yes. Yes.
and therefore in this interpretation we see that surface tension of a liquid is equal to the surface energy per unit surface area, right?
Yeah. Yeah.
Yeah.
So both the interpretations are equivalent. It's just that one is in terms of forces, one is in terms of energies, right?
Yeah.
S is F by L also and U by A also, right? So this is fine. Look at example 14.5. A water drop of radius this much is broken into 1,000 equal droplets. Calculate the gain in surface energy. Surface tension of water is 0.0475 Newton per meter, right? So
Mm-hmm.
first he says water drop of radius this much. So volume of the water drop you can find out.
Yeah.
So
Yeah.
Yeah.
so afterwards it is breaking up into 1,000 smaller water droplets, right?
Yeah.
Yeah.
So volume will remain conserved. Of total water's volume will be same because the
Yeah.
original drop is breaking into smaller drops, right? So radius will become 1 r by 10, right? Because it is 1 by 1,000, right?
Right.
Yeah.
Right.
Yeah.
So new radius is basically r by 10 when original radius was r, right?
Yeah.
So surface area of the original drop is 4 pi r square, capital R square. And surface area of the 1,000 droplets will be 1,000 into 4 pi into small r square, right?
Yeah. Yeah.
Which is basically r square by 100, capital R square by 100. So it becomes 40 pi r square, right?
Right. Yeah.
So the increase in area is 40 pi r square minus 4 pi r square, right?
Right. Yeah.
Yeah.
So that is 36 pi r square.
36.
So gain in surface energy will be surface tension into gain in area, right?
Yeah.
Right. Yeah.
Yeah.
Del U will be del S into S into del A. So del A we know 36 pi r square and S value we know. So then you can calculate the increase in energy of the system during this process of a drop breaking into droplets,
Yeah.
right? It
Yes. Yeah.
depends on, finally for increase in energy, you have to use this interpretation of surface energy, right? Correct?
Yeah.
Yeah. Yeah.
Now, so that is basically the theory of surface tension. Now we look at some other things, some other applications of it. So one of them is excess pressure inside a drop, which is 14.11, right? Now we'll focus carefully on what is happening and how he is explaining in this book. So excess pressure, how he derives it. Okay. So let's see. Inside a drop. Now let us consider, he's saying, let us consider a spherical drop of liquid of radius capital R. He has drawn that in figure 14.17, right?
Yeah. Yeah.
If the drop is small, effect of gravity can be neglected and shape is assumed to be spherical, right? So, okay, otherwise if the drop was large, then gravity will distort the shape, right?
Yeah.
Mm-hmm.
Because there will be a lot of weight there. So a lot of force of gravity. So the drop might only collapse on the weight of gravity, right?
Yeah.
So we are not considering those complications. So right now, he's saying imagine a diametric cross section ABCD. ABCD is a plane through the center of the drop, okay? And it is a diametric plane. Do you understand what that means?
Yeah, yeah.
So this is the center. You create a plane like this, a circle basically.
Yeah. Mhm.
This is a circle ABCD, which basically divides the sphere into two hemispheres, right?
Yeah, yeah.
Yeah. Yeah.
The surface of the two hemispheres touch each other along the periphery of A, B, C,
A,
D.
B, C, D.
A, B, C, D, A. So basically, you can now think of it as two hemispheres which touch each other where? They touch each other on this periphery, right?
Yeah, yeah.
Yeah.
This periphery is ABCDA, right?
Hmm.
Okay. Okay. So now each hemispherical surface will pull the other surface due to surface tension. No.
Yeah, yeah.
Now
Yeah.
this has a mass of liquid or bulk of liquid, right? And
Yeah.
this has a bulk of liquid, but the surfaces are in contact here. This surface is in
Contact.
contact with this surface, right?
Yeah.
Yeah.
So each surface will pull each other, pull each other along that ABCDA contact line, right?
Yeah, yeah.
Yeah. Yeah. Yeah.
Now consider the equilibrium of the hemispherical surface ABCDE. Okay, so this is the left side on the figure. ABCDE is the hemispherical surface, right?
Yeah.
Correct. So forces acting on this are F1 due to surface tension of the surface ABCDG, ABCDG on which is in contact. So F1 is the surface tension force due to this surface, right?
Yeah, yeah.
Correct. Because it is going to be pulled, no, by the second surface.
Yeah.
The right side will pull this, right, with some F1, right?
Yeah. Yeah.
Then F2 is due to the air outside the surface ABCDE. So air outside will be exerting some pressure,
Right, yeah.
right? And F3 is due to the liquid inside the surface ABCDE. So F3 he's saying is liquid inside the surface ABCDE. So that will be some internal pressure, right?
Yeah.
Mhm.
Some internal pressure type of thing from the liquid inside, which will be in all directions, right?
Yeah.
Yeah.
Correct. So what he's saying is force due to surface tension acts on the points of the periphery ABCDA, right?
Yeah, yeah.
Force due to surface tension only acts on the boundary, on the line that divides two portions, right? So
Mhm.
here that is the
Mhm.
periphery ABCDA. So the force on any small part DL of this periphery is S into DL and acts parallel to the symmetry axis OX. So if you think of a small part here on the periphery, the surface tension force will be S into DL, right? And it
Yeah,
will be
right, yeah.
parallel to the x-axis, right? The x-axis is somewhere here, right? Because this plane itself was perpendicular to that and in a diametric plane, right?
Yeah, yeah.
So any point on the
Yeah.
surface tension pulls it to the right, which is plus I, right?
Hmm.
Which is
Plus.
parallel
Yeah.
to the line OD or something, right? Parallel to that
Mhm.
OX line, right?
Yeah, yeah.
Yeah. Yeah.
The
Yeah.
resultant of all the forces due to surface tension will be integral of SDL, and S is constant. So integral of DL is just the line surface where it is touching. So that
Yeah.
Right.
is the
Yeah.
perimeter. So S
2
into
pi
2
r.
pi r, right?
Yeah.
S into
Hmm.
2 pi r is the resultant forces due to the right due to the other part, right?
Yes, yeah.
Yeah.
Now, so that let's call it F1. Resultant is S into 2 pi r. Now, consider the forces due to the air outside the surface A, B, C, D, E, right? So how does air affect it? It will hit on all portions of that hemisphere, right?
Hmm.
Yeah.
And it will try to push with air pressure, right? There.
Yeah, yeah.
So he's taking a small part delta S of the surface as shown in figure 14.19. If the pressure just outside the surface is P1, the force on this delta S will be P1 delta S along the radial direction, right?
Right, yeah.
Yeah.
Right.
Hmm.
And since it is a proper hemisphere, all of the P1 delta S and all from different portions, right, of the hemisphere will all point to the center, right? Because then
Yeah.
only you'll be tangent
Center,
to
yeah.
the plane, right?
Right, yeah.
So all of them are radial type of forces on this due to the air, right? Now, if that happens, we can say that the resultant of all of these radial forces will be along the x-axis only, right?
Yeah.
Yeah, right.
Resultant of all of these forces will be along the x-axis, right? OX.
Yeah, yeah.
Correct. So that is what he's saying. He says if by symmetry, the resultant of all such forces acting on different parts of the hemispherical surface must be along OX. Now, if the radius through delta S makes an angle theta with OX, right?
Yeah.
Suppose radius through delta S, which you drew so that you could attract the. So what we are just saying is that if that radius line is at an angle theta, right, to the OX, right? Then the component of P1 delta S along OS will be P1 delta S cos theta, right?
Yeah, yeah.
Yeah.
Obviously, P1 delta S cos theta,
Delta S.
right? Now, P1 delta S cos theta is the external force. Now, you can just think of this as delta S cos theta into P1, right?
Yeah,
What is
yeah.
delta S cos theta? If there is a tiny cross section here, what is the projection of it on the diametric plane? What is the portion of it which is perpendicular to the diametric plane, which is in the plane of the diameter, right?
Yeah, yeah.
Yeah.
Basically, projection of that area. Or if you don't want to think of that, think of just that the forces were in this direction, right? So you have to take component like this, right?
Yeah,
Right.
yeah.
Or think of it as force of pressure of P1 was acting on this tilted area, but instead of tilted area, we can say projection of a straight area where you can just directly multiply, right?
Yeah.
Right, yeah.
Tilted area was tilted at some angle, so delta S cos theta is the projection on this diametric plane, right?
Yeah.
Yeah.
Correct. So P1 into delta S cos theta is the force due to the air pressure on the delta S, right?
Yeah, yeah.
When components of all the forces P1 delta S on different delta S are added, we get the resultant force due to the air outside the hemispherical surface, right? So basically, if you keep doing this addition for different delta S, think of it in the projection method. What will eventually happen is that the delta S cos theta will keep getting projected on the diametric plane, and eventually area of that ABCDA is going to matter, right?
Yeah, yeah.
Yeah.
When you add up all the P1 delta S cos theta, so on, right?
Right.
Yeah,
Ultimately, you
yeah.
will add up the projections and it will become the whole ABCDA face area, right?
Yes,
Right.
Right? So resultant due of force due to the air pressure from outside will simply become P1 into pi r square from outside, this resultant force, right?
Yeah, yeah.
Right, yeah.
Okay. So similarly, resultant force on this surface due to liquid inside, liquid will also exert some similar resultant forces. And since it is a hemisphere, liquid will also have similar behavior on this line, right? It could exert forces in multiple directions, liquid here, right? And
Yeah.
eventually the resultant will become again P2 delta S
Yeah.
cos theta. So it will become P2 into pi r square, right? Due to the
Yeah.
pressure inside the
Yeah.
liquid. P2 into pi r square. Think of this liquid as just another type of air, right? If air was P1 and P1 was coming P1 into pi r square, then this will also come similarly, right?
Yeah, yeah.
Yeah.
Now, for equilibrium, we should have these two forces, right? Which forces? F1 plus F2.
F2.
F1 was what? F1 was the surface tension force, right?
Right,
Yeah.
yeah.
And F2 was this push from outside, right?
Yeah.
Correct. Should be equal to F3. And F3 is what? F3 is the pressure force, right?
Right.
F3 is due to the liquid inside, right?
1 second, let me just check once. Resultant force on the surface due to the liquid inside. Mm, This force will be in the direction OX dash. OX. Oh, he's saying due to the liquid in the other side. His direction of that force is coming as OX dash, right? OX dash is opposite side.
Yeah, yeah.
So
Yeah.
OX dash is opposite side. This is F3. So that means he refers to which liquid? The liquid inside from here exerting a force, right?
Oh,
Right.
okay, okay. Yeah, yeah.
Because internal forces cannot, if you are doing free body diagram of something, you cannot take internal forces.
Mm-hmm.
You only
Correct,
care
yeah.
about the external forces on it, no?
Yeah.
Right. So there is one surface tension force which is external to this system, right?
Yeah.
Yeah.
Surface tension force is external, but there is liquid pressure from this side which is external also, right?
Yeah, yeah.
Yeah.
And there is air pressure from this side which is external, right?
Mm.
So ultimately now you will get air pressure force is this side, P1 into pi r square, right? And liquid pressure force is from this side, P2 into pi r square, right?
Yeah. Yeah.
And surface tension force is like this, so S into 2 pi r, right?
Right, yeah.
So these forces should be in equilibrium for equilibrium of that whole semicircle, this portion, right?
Yeah.
So you should have P1 into pi r square plus S into 2 pi r is equal to P2 into pi r square,
Yeah.
right? So therefore you get P2 minus P1 pi r square is equal to S into 2 pi r, and you can divide by pi r square here, pi r square here, remove this, pi cancels, and this becomes 2s by r, right?
Yeah, yeah.
So what you end up getting is P2 minus P1 is equal to 2 surface tension by r, right?
Right, yeah.
Now what is the meaning of this? The meaning of this is that the pressure inside in the liquid which was pushing it here, right? Pressure in the liquid here is higher than the outside pressure by a factor of 2s by r,
2x.
correct?
Correct, yeah.
So the radius is smaller, the difference in pressure will be bigger. If it's a small drop, the pressure difference will be quite high, inside pressure and outside pressure, because radius is small, so 2s by r is large,
Yeah.
right?
Yeah.
If
Yeah.
it is a bigger drop, then it is not so high, the difference in pressures, right? So he's saying the pressure inside the surface is greater than the pressure outside the surface by an amount of 2s by r, right?
Yeah.
So below, it's important to understand what he's saying. In the case of a drop, there is liquid on the concave side on the surface and air on the convex side, right?
Mm-hmm.
So in the case of a drop, think of a drop in air, right? So
Yeah.
water droplet in air, right? So there is, this side is the concave side, so there is liquid inside, right? Liquid on the concave side
Concave.
and air on the convex side, right?
Right.
Air on the convex side. Okay. Now we have figured out now that inside pressure is greater than outside pressure. So basically pressure on the concave side, P2, is greater than P1 by a factor of 2s by r, right?
Yeah, yeah.
This is what we have understood. So pressure on concave side is higher, only then the drop has become that concave shape, right?
Concave shape.
Because that means the inner thing is pushing it more, right? Pushing it out more, right?
Yeah.
Yeah, yeah.
Yeah.
The result is true in all cases, that pressure in the concave side is higher than pressure
Higher.
in the convex side. Now he says if we have an air bubble inside a liquid, a single surface is formed, right? Air bubble. So there's just a layer of air, right? So one surface is formed inside a liquid. There is air on the concave side and liquid on the convex side, right?
Yeah. Yeah.
The pressure in the concave side is greater than the pressure in the convex side, again by an amount of 2s by r, right?
Yeah, yeah.
So he's talking about air bubble in a liquid. Now you have to think about excess pressure in a soap bubble. soap bubble, what happens is it's not a simple bubble because there's a film of soap which itself has a lot of thickness.
Yeah.
Inside
Yeah.
there is air, there is a soap film here, and outside there is air, right?
Yeah.
Yeah. Yeah.
This is a soap bubble, right? It has two layers now, right?
Hmm.
Hmm.
Correct. So what you can say is that if I have this situation, let's say inside pressure was P2 and outside pressure in the film of the soap it was P dash and outside was P1, right?
Yeah.
Yeah.
So everywhere you can say between this and this concave surface you can have P dash minus P is equal to 2S by R, right?
Hmm.
Correct. And similarly,
Yeah.
between this and this convex surface, concave surface, you can have P2 minus P dash is equal to 2S by R, right?
Right. Yeah.
So therefore, combining these two, you will get P2 minus P is equal to 4S by R.
R will be different in both the cases, right?
Huh,
But then
it
the difference will be
depends.
very
Yeah.
small. So
It depends. In this case, the difference will be very small, so that's why we are using the same R.
yeah.
Technically, it is different, right?
Right.
Yeah.
Yeah.
But very slight difference because of that. The pressure, so what we see here though is that the pressure inside a soap bubble or something, right,
Yeah.
is different from the outside pressure by 4S by R rather than like in a drop, right?
Yeah.
In a
Yes. Yeah.
drop, it was 2S by R,
Two
right?
as well.
Because there was only one layer.
Yeah.
And here, because of a soap film, there are actually two layers here, right?
Right.
Yeah.
Pressure difference is 4S by R here, right?
Yeah.
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 Now we'll discuss this contact angle stuff, okay?